Now, the next part asks us to find how that value relates to the modern value. So if we take that value for delta Cepheid, which is the modern value, and we compare that to the distance SMC based on Levet's measurements, we can get an answer. So we know that the distance to the SMC is equal to the ratio of the distance to the SMC divided by the distance to delta Cepheid times the distance to delta Cepheid. Notice that these two would just cancel right out. But we know this ratio, and we know this. So that's equal to, well, we got this ratio way back earlier. See? The SMC is 140 times further away than delta Cepheid, and that was part B. So we know that this is 140, and we just got the distance to delta Cepheid in the last part of the question, which was 265 parsecs. Now we can take our calculator and we can say 140 times 265 equals 37,000. And it asks to express the answer in kiloparsecs. So 1,000 parsecs is a kiloparsec, so that would be equal to 37 kiloparsecs. So if you take the modern value for delta Cepheid, her value would be 37 kiloparsecs. Now, the modern value to the SMC is 60 kiloparsecs. So you can see that she was off by a little less than a factor of 2. Similarly, if we look at part H on the same page, it asks how far away would Hubble have measured M31 to be if he knew the distance to delta Cepheid. How does this compare to the modern value of 780 kiloparsecs? Well, recall from the part with Hubble that Hubble thought that the distance was 1.1 times the distance to the SMC. So we will then take that the distance to M31 equals the distance to M31 divided by the distance to the SMC times the distance to the SMC divided by the distance to delta Cepheid times the distance to delta Cepheid. Now Hubble relied on Levet's data, and he measured this ratio. So he measured that ratio to be 1.1, and then this here ratio, as we just said before, was measured to be 140, and this here was measured to be 265 parsecs, and the product of this and this we already calculated was 37 kiloparsecs. we get 40. Now, this is nowhere near the modern value of 780. And notice it's nowhere near by over a factor of 10. Now, part of that is because of this value here, and part of that is based on his measurements. So we want to figure out what he would have gotten if he actually knew the distance to the SMC perfectly. That would be 1.1 times 60, which is 66, which is still nowhere near 780. So you can see that based on his data, the distance to Andromeda Galaxy is about a factor of 10 closer than it would have been than our modern value. So why do we care so much about Edwin Hubble measuring this? The reason is that this was the first solid evidence that the Andromeda Galaxy was outside of our own Milky Way. That's right. Everything was smaller, except for the Milky Way itself, but it was the first evidence that it was outside the Milky Way. But it was not as definitive as people often make it out to be. Now, the last part of this sheet is something for you to do after doing the reading. But it points out that there was somebody named Walter Baade who pointed out in 1952, and there's a citation to Ferris, that Hubble had been confused about different types of variable stars. So, everybody knows that Hubble was confused about different types of Cepheid variable stars. Nobody's really sure about whether Leavitt was or not. And so, based on your data here, and based on what you figured out, who was more wrong? Was it Leavitt or was it Hubble? And if so, could this explain it?